Hi there, and thank you for tuning in to this midterm solution video. Let's get started. So the first problem, you have this boundary value problem, and you should recognize this, that we've done these before. The solutions are going to be sines and cosines. Exponentials are not going to satisfy these boundary conditions. So y double prime, so part A, y double prime equals negative omega squared y. You got to figure out what omega is. So of course this is sines and cosines, so y of x equals a cosine of omega x plus b sine of omega x. So this first boundary condition is going to kill off the sines, so we can see that y prime of 0, so you take the derivative, the cosine, or if you take the derivative, this becomes a sine, you plug in 0, that goes away, this becomes a cosine, so you get b omega cosine of 0 equals 0. So that tells us that b has to be equal to 0. So we get that y of x equals a cosine of omega x. Now we use our second boundary condition. Y of 6 equals a cosine of 6 omega equals 0. Of course, that happens. Cosine of 0 at half integer multiples of pi. So that means that 6 omega equals n plus 1/2 pi. So that means that omega equals n plus 1/2 pi divided by 6. So that means that the eigenvalue, which is lambda, which is omega squared, lambda n, let me call this n, equals n plus 1/2 pi over 6 squared. Now I say find the four smallest one of these because I didn't want to tell you whether it was starting at n equals 0 or n equals 1. So lambda 0 is, so when n equals 0, we do get a value. We get pi over 12 squared, and we get that yn, or y0 of x equals cosine of pi over 12x. Lambda 1 is 3 pi over 12 squared. Y1 of x is cosine of 3 pi over 12x. Lambda 2 is 5 pi over 12 squared, and y2 of x is cosine of 5 pi over 12 x. And finally, lambda 3 is 7 pi over 12 squared, and y3 of x equals cosine of 7 pi over 12x. Now, if you gave me, as for eigenvalues, if you gave me megas, I think I took up a half a point because it's, that's not the eigenvalue, but if you got this far, you got most credit. So you got to sketch these things. So let's do that. So if this is 6, then the first one is like this, the second one is like that, the third one is like this, and the fourth one is going to be like that. So all of them have to be flat here. They go through 1. All of them have to go through this point. Now, some of you put a's in front or constants in front of this. You don't need that. I like to just make the constant equal to 1. It's not wrong, but I think it's slightly neater if you just let the constant be equal to 1 and say these are the eigenfunctions. Okay, part B. Define an inner product under which these are orthogonal. So for that, f of x, g of x. So you have to define what this is. This is the integral from 0 to 6, f of x, g of x, dx. Some of you put a constant in front of here. That's not wrong, but you don't need it. It's going to be orthogonal regardless as to what constant is in front of here. And some of you also put a complex conjugate, a bar over here. That's not wrong either, but I did say real value function, so the complex conjugate of a real function is itself, so you certainly don't need it. Now, the reason why we put a constant like 1 over L or 1 over 2L for classic Fourier series is because we do that so the functions become orthonormal instead of just orthogonal. I'm not sure what constant you'd need here to make these orthonormal. I'd have to check. I mean, well, actually, I can tell you what constant from part C. So x squared minus 36, sketch this. So that it's just a parabola. It's x squared minus, it's x minus 6, x plus 6. So it intersects negative 36 here and 6. A lot of you missed this. It's just basic algebra. I guess it's a good thing that you're doing the advanced calculus and ODEs better than some of the middle school, high school algebra. I try to make this something that everybody would get. But I have said that sometimes the algebra is the hardest part of this class, and that's both good and bad. I mean, that means stuff isn't as bad as it isn't as hard as it often is made out to be seen. Okay, so this thing we have to write Cn as a linear combination of the eigenfunctions. So Cn is just the inner product of x squared minus 36 with yn over yn. And I'm not going to write this in terms of an integral because I've defined the integral right here. Now, some of you have to divide by a constant here. I don't know actually what constant would make that orthonormal, but well, one answer is whatever the heck this constant, whatever this is in general, that's going to probably be some constant. If you divide by that, then these functions become orthonormal, and then for your CNs, you don't need this because it's equal to 1. You just write this. Okay, so let's do part 2. We have a PDE. So first of all, part A, describe what this models. There's 4 parts of it. This is the heat equation. So we are modeling the temperature of a bar of length 6. This boundary condition, the UX, means it is insulated at the left endpoint, and the right condition says that it's 0 degrees at the right endpoint. So this is x equals 6. And finally, the initial condition says that the temperature of the bar is given by this function right here. So initially, so that means that you have something like, so this is negative 36. And then what's going to happen well, I'll come back to that. Okay, so next we assume there is a solution f times g. We plug this back in and we separate variables. So we've done this before a lot. So this is f g prime equals c squared fg. So we divide by c squared fg, and what we get is we get g prime over c squared g equals f double prime over f, and that is equal to some constant, which I'll call negative lambda, to make it match up with this. And now what we get is we get f double prime equals negative lambda f, and these boundary conditions are going to give us that f prime of 0 equals f of 6 equals 0, like we did in lecture many times. And so we also get g prime equals negative c squared lambda f. So here are our 2 differential equations. This is a boundary value problem for f, which we solved in part 1, problem 1, and this is, oh, sorry, that should not be f, that should be a g. Sorry about that. And that, you look at this, you think exponential decay. Okay, so what we have is we have fn of x equal, well, I don't need to rewrite it. Well, actually, you know what? I didn't actually write it up here, so, or did I? So I have, yeah, let's write it down. So fn of x equals cosine of n plus 1/2 pi over 6x. And lambda is what lambda is up here. So that means that your general solution is going to be the infinite sum of n equals 0 to infinity. So we're going to start at 0 because we get non-zero eigenvalues here of, let's call it an, cosine of n plus 1/2 pi x over 6 times e. The solution solution to this is going to be exponential decay, so that's going to be e to the negative c squared times lambda this times t. So let's take this. So let's write that as c n plus 1/2 pi over 6 quantity squared t. So I stuck the c squared inside and just made it c. So this is our general solution. And then the particular solution that satisfies the initial condition, just as always, you plug in t equals 0. So you get u of x 0, and of course what's going to happen is the exponential goes away, and you get n equals 0 to infinity, an cosine of n plus 1/2 pi x over 6 equals x squared minus 36. And that is exactly what we did in part C in the previous problem. So we now have a solution for the ANs. AN is just going to be the inner product of x squared minus 36 with this cosine term, which I'm just going to call Fn, because it's the nth eigenfunction, divided by Fn, inner product of it with the self. Now I said involving an integral, but it's perfectly fine to write it like this because I've already told you how this inner product is defined, so I don't need to rewrite that. And that's it. What's the long-term behavior of this system? Well, if you have insulated bar here and it's open and 0 degrees here, then this is going to eventually flatten out. The heat will all escape through the bar and it will approach even 0 degrees. So that's the physical justification. The mathematical justification is that this exponential functions, as t goes to infinity, goes to 0, so this whole function goes to 0. So either way, the long-term behavior is going to be, the bar is going to go to 0 degrees uniformly. Okay, problem 3. We have the function cosh defined on 0 to pi, and sketch the even and odd extensions. So let's do both of them here. So I didn't expect you to remember what cosh looked like. That's why I said it's the shape of a hanging chain centered at 0. So it looks like this. So that is 1, because remember cosh and cosine are the same at 0. I also reminded you about that. So the even extension means that you make it even, and then you make that periodic. So that's what the even extension, let's see, that's pi, that's 3 pi, yeah, that's 5 pi. Then the odd extension is you take this and you make it odd, and then you make that periodic. I guess I did a little more than I had to, but it's a little bit harder to draw than the last one, but I think you get the idea. So I drew a little more than 5 pi there, that's okay. Okay, next, compute the Fourier cosine series. So the Fourier, so an is 2 over pi from integral from 0 to pi of this guy. And so that's just this thing here, evaluated from 0 to pi. So if you plug in, first of all, if you plug 0 into sine, you're going to get 0. And same with well, let me just write it like this. So sine of n pi equals 0, and sine of 0 equals 0. So when you plug these guys in here, you plug pi into here. I forgot to say this is 2 over pi because I put the 2 over pi there. So we are going to get 2, let me pull out everything. So 2 over pi n squared plus 1. So I'm going to plug pi into here, and I get sinh of pi times cosine of n pi, which is -1 to the n. And now when I plug pi into here, I'm going to get 0 because sine of n pi equals 0, so I can ignore that. Now I got to subtract 0, and I plug 0 into here. Sinh of 0 is equal to 0. Remember, sinh and sine at 0 are the same, so I can ignore that. And then when I plug 0 in for here, I can ignore that because sine of 0 is 0. So all of these others, so I basically get this plus 0 minus 0 plus 0. And so I just get this thing right here. Now a naught is 2 over pi, 0 to pi, cosh of x dx. And remember, cosh and sinches are derivatives of each other, so therefore they're integrals of each other. If anyone had forgotten that, that's something that I would have been happy to tell you. I think one of you said you didn't know what it meant. Just ask. That's not something, again, I don't want you to lose points because you didn't memorize what that was. I think most of you knew, but again, I don't want to penalize you. So don't hesitate to ask questions if you have them. So 2 over pi, sinh of x from 0 to pi. So remember what sinh looks like. Sinh is, it's only 0 at 0. So this is going to be 2 over pi times sinh of pi minus sinh of 0 is like that. So then the Fourier series is f of x, or cosh of x, is a naught over 2. So that is sinh of pi over 2 plus n equals 1 to infinity of 2 over pi n squared plus 1 sinh of pi negative 1 to the n times cosine of nx. Okay, now several things. A couple of you said all the bn's are equal to 0 because cosh is even. That's actually not why. It's because we are computing the Fourier cosine series. So we're literally taking the even extension and computing the Fourier series of that. So if we had started with a sinh wave, or not a wave, a sinh function, which is something like, so if we had started like that, we still could have taken the even extension, and even though sinh is odd, the bn's would be 0 because we're taking the Fourier cosine series. So just want to make sure that you had the right reason. Other than that, I think people did pretty well on this problem. For this one, a couple of you had this thing shifted down, so I went to the origin. I think I took off a half a point. If you did that, mostly because I said cosine and cosh are the same at 0. And yeah, I think that's about it. Okay, problem 4. Let A be a linear map on a vector space equipped with an inner product. Recall that one consequence of this is that, I didn't say what this is, but that V has an orthogonal basis of eigenfunctions. You should know that for that has to be true, we need A to be self-adjoint. So I should have said A is explicitly said that it's self-adjoint up here. I do say it is here in part A. So part A, what does that mean? That means the inner product of A, V, and W equals the inner product of V and A, W for all V and W in V. So I understand that it's not, from here, it's not necessarily clear whether or not I'm assuming that A is self-adjoint in B, C, and D. I had intended that, but I will be generous in grading this based on your assumption. And because you have to explain why your answer is yes, it should be clear from your explanation what your assumption is, and I will grade accordingly. If your answer is no, give an explicit counterexample, and if your counterexample is consistent with that assumption, you will get full credit. Okay, so for part B, so if you did not assume that A is self-adjoint, then it's certainly not true that every basis is orthogonal, because if you take a non-self-adjoint map, it does not necessarily have to have orthogonal eigenfunctions. But if you do assume that A is self-adjoint, then it's also not necessarily true that every basis consists of orthogonal eigenfunctions. So for example, if A is, so this is an example from last year's midterm that I gave you for practice. If A is just the identity map, then that means that A, or I times V equals V for all vectors V. So that means everything is an eigenvector, with eigenvalue 1. every single vector gets scaled by 1. So if v is equal to R2 and everything is an eigenvector, then we are guaranteed that there is an orthogonal basis. But there are bases like 1, 0, 1, 1 that are not orthogonal, and that's the basis of R2. So the answer for B, no matter how you interpret it, needs to be no. Part C, does this necessarily mean that there is a basis consisting of orthonormal eigenfunctions of A? So anytime, now I did say here, I think that you have an orthogonal basis of eigenfunctions. So regardless how you interpret it, if you have an orthogonal basis of eigenfunctions, what I'm asking you here is, can you make an orthonormal basis? And the answer is absolutely yes there. So answer is yes, because if v1 up to vn is orthogonal, then v1, then if you normalize, then that's the key, vn over the norm of vn, this is orthonormal. And then finally, D, it doesn't matter what the assumption of A is. I give you an explicit linear map, and I say, is the standard differential operator self-adjoint? And so if the answer is yes, then what does that mean? So the question, well, I should say it this way. Is the derivative of inner product of the derivative of f and g equal to, yes or no, the inner product of f and the derivative of g? So what is that saying? So I'm asking you, is it true that the integral from 0 to L of the derivative f prime of x, g of x dx, is this yes or no equal to 0 to L times f of x times g prime of x? Is this all true for all functions? Yes or no? And the answer, it'd be amazing if it were true. That's a formula you would have learned about in calculus, but this is definitely not true. Now you need to give an explicit example. You can't just say this. No, this is not always true. So what's an example? Well, let's take one where the derivative is 0. So what if like f of x equals 1 and g of x, I don't know, is anything else like x squared? Then, well, the left-hand side is going to be 0 because we have 0 times x squared. Integrate that. The right-hand side is going to be 1 times 2x from 0 to L. That's going to be non-zero. Okay, problem 5. We have a square wave defined as follows. Let me first actually sketch this. No, that's part of part B, but I think it helped sketch it first. So let's see, 1, 2, 3, 4, 5, 2, 3, 4, 5. So this is pi. So the square wave is defined to be 1, but at 0 it's equal to 0, and so it's going to look like that. And then it just alternates like this. So the left endpoints are all open, and the right endpoints are all closed. So I'll do a couple more of these. I think I did that right. Okay. So next, compute the complex Fourier series. So this is f of t. So first of all, C naught is the average value. You could just look at that and you could say it's 1/2 right away just by inspection. If you didn't see that, well, you can compute it directly as 1 over 2 pi from negative pi to pi of f of t dt. Now you got to be careful. You can't just stick 1 in here because it's 0 on this part. But what you can do is you could say this is 1 over 2 pi, 0 to pi. F of t now is just 1 dt. So this is the area under the curve. Well, you could just say it's 1 over 2 pi times t from 0 to pi, which is equal to 1/2. Okay, so Cn is 1 over 2 pi. Okay, again, from negative pi to pi, f of t e to the negative I n t dt. And once again, we can say it's 0 to pi times 1 times e to the negative I n t dt. Okay, so now this is 1 over 2 pi I n, because again, this is the exponent, negative I n pi, so we got to divide by that. And so we get e to the negative I n t from 0 to pi. So if you plug in pi, you get negative, let's see, so negative 1 over 2 pi I n. Plug in pi, you get negative 1 to the n. You plug in 0, you get 1. So this is 1 minus negative 1 to the n divided by 2 pi I n. So that is Cn. You don't need to write this if you don't want to. I mean, of course, this is equal to 1/2, and this is equal to what we just found. Okay, so that's part A. Part B, you need to sketch both the function itself. We just did it right here. So let me do that. And then we also have to sketch the Fourier series. And as I said, they only differ at the endpoints. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So here, the difference is that we don't have any. Remember, we don't have any control as to what the function is at the endpoints. Maybe I should have made this a little bigger. And what it always ends up being is half of it's the average of the discontinuity. So this is up here. And so what that always ends up being is it's this dot right in the middle. So if you take this Fourier series and you actually plot it, and you plug in the value at the endpoints, at the discontinuities, you actually get this average value. Okay, so that's part B. And then part C, solve this initial value problem, where f is the square wave above. So the first thing you should do is y of t equals yh of t plus yp of t. And yh of t, so this thing here solves yh double prime plus 4yh equals 0. You should right away recognize this immediately, that yh of t is a cosine of 2t plus b sine of 2t. Now, some of you went through and did e to the rt and derived it and got the right answer, but again, I want you to spot this. I want you to notice this by inspection. I've said this before. It will keep coming up. Some of you got it the right way. Some of you got it the wrong way. So some of you left it as c1 e to the negative 2it plus c2 e to the positive 2it. I didn't take off for that, but it's much better just to do sines and cosines. Okay, so for your particular solution, we have to assume that the solution has the same form as the right-hand side, like we did in lecture there. So the right-hand side, we know, is a Fourier series. So that means that we have to assume that yp of t is c naught. So again, I like to take the constant out here because all of these positive or negative are the same, or you just use the same formula for, but you got to compute the constant separately. So c naught plus all the non-zero cn's, cn e to the I n t. So we don't know what the coefficients are, but we assume that there's a particular solution that is a Fourier series. So we take this guy and we plug it back into the left-hand side. So to do that, we have to take two derivatives. So yp double prime. So take two derivatives, you get, the constant goes away, you get, let's see, so you get an I squared, n squared pulling out. So I squared is negative 1 times n squared cn e to the I n t. So now we can say y double prime plus 4y equals f of t. The left hand side, so y double prime is negative n squared cn e to the I n t. 4y is again, this is our particular solution we're plugging back in. So 4 of these plus 4 C naught plus 4 Cn e to the I n t equals f of t, which is this guy up here. So that equals 1/2 plus 1 minus negative 1 to the n over 2 pi I n e to the I n t. Again, this thing here is f of t, our answer, part A. So we collect terms, and on the left-hand side, we get the sum of, well, let's say 4 C naught. Let's pull that out front. So now we have 4, 1 minus, no, how about this? 4 minus n squared Cn e to the I n t equals 1/2 plus basically the same thing here. I don't know, do we need to rewrite it? Yeah, let's do it. N over 2 pi I n e to the I n t. So we have to equate coefficients. So this 4 C naught has to be equal to 1/2. Those have to be the same. So we get that C naught equals 1/8. And we also get that this coefficient of e to the I n t has to be equal to that coefficient of e to the I n t. So in other words, we get that Cn equals 1 minus negative 1 to the n over 2 pi I n 4 minus n squared. So our final solution is A cosine of 2t plus b sine of 2t plus our particular solution, which is 1/8 plus 1 minus negative 1 to the n over 2 pi I n, I'm running out of room, 4 minus n squared e to the I n t. So that is our final, that is our general solution. Now before we get to the, let's just say something about these initial conditions first. Let's skip to describe a physical situation that this could model. So when you see, so make sure to describe the left and the right hand side. So the left hand side, you should look at that and think that is simple harmonic motion. For most of us, that's a mass spring system. If you're an electrical engineer, you might like, it's an RLC circuit without resistance. To me, that I don't have everyday knowledge with an RLC circuit. To me, it's much more intuitive to think about a mass spring system and something like that's a simple harmonic motion like that. So what does this model? This could model a mass spring system where the forcing term is given by this square wave. Now, admittedly, I guess it's more natural for a square wave to appear in a electrical engineering scenario than a mass spring system, but let's just go with it. So the forcing term is this square wave, and this says that initially the mass is at equilibrium and at rest. Both of these are 0. Okay, so you got 2 points for describing that. You got, I think, 4 points for doing this differential equation. I think 2 points for graphing, 2 points for graphing these two, and then I think you got, I think I did 4 points for solving this, or for this actual series as well. So 4 points for this, 2 points here, 2 for the physical situation, and 4 for this. Now, I also said find the particular solution, solve the initial value problem. So use these initial conditions to find A and B. Upon doing it, I realized that this was actually harder than I intended. I was thinking that one of these would right away make one of them be 0, but it's actually more complicated than that. So I didn't actually grade that on the exam. But let me actually show you. Yeah, why not? Let me show you how to do it. I think it's definitely harder than I intended it to be, or I guess messier. So let's let's plug this initial condition in, y of 0. So y of 0, if we do that, I'll show you why it's harder than I intended. Y of 0 equals a cosine of 0 plus b times 0, so that's plus 1/8. So a plus 1/8, and then plus you got to type 0 into here or plug 0 to here. That makes this go away, and now what we get is we get this infinite sum. So we get 1 minus negative 1 to the n over 2 pi I n 4 minus n squared, where n, this is a doubly infinite sum. It's bidirectional. And this is a number. I don't know what number is. It's a number. So this thing equals 0, and now this tells us that a equals the negative of these two things. So a equals negative 1/8 minus that sum, 1 minus negative 1 to the n over 2 pi I n, whatever the heck this number actually is. And then similarly, this second initial condition here, if you take the derivative of this thing, this is, again, it's messier than I expected it. So if you take the derivative of this thing, y prime of 0, the derivative of cosine becomes a sine. So you plug 0 to here, that goes away. So you get 0, and the sine turns into a cosine. The 2 pulls out, so you get 2b cosine of 0. And then the 1/8 goes away, and now the derivative of this, an in, pulls out. And so you get the sum of 1 minus negative 1 to the n divided by the in pulls out and cancels. So you get 2 pi 4 minus n squared equals 0. And now that tells us what b is. So b equals this sum, 1 minus negative 1 to the n over 2, I should say over 4, because we have 2b there, so over 4, and it's negative 4 pi 4 minus n squared. So a couple of you actually did this with the motions and did this, and you know, I think those of you who did really well in the exam anyways, so you know, I think you still did well, but for the rest of you, I just didn't grade this. It ended up being messier than I thought, and I think if you got to the point where you knew it was a homogeneous plus particular, you got the right homogeneous solution, and you knew how to find a particular solution, plug it back in, and find the coefficients and equate things. At that point, I'm like, you know, you deserve the 4 points for solving this thing, and I stopped there. Okay, so if you have any questions on this, please let me know. As I said in my email, I was very impressed. This is a hard exam. Like, no, I think the highest score was 48.5. It is like whack-a-mole. You just can't get every single little detail right. Like, there's multiple people who got for any problem, there was multiple people that got it completely right, but nobody got everything right. It covers a lot of material. This is advanced. It's not only advanced of how to solve this, but it's very theoretical as well. And I mean, I have taught some baby parts of this in my ODEs class to honor students, and I think you guys did as well or better as they did. So I'm impressed with how everyone did. Clemson students, as I said, are really, really smart. So, okay, there's one more week left. Please let me know if you have any questions. Remember, if you get an A or a B on the final, you get at least that in the class, and every single one of you is capable of getting that. So take advantage of my offer to help. I will hopefully see you sometime next week.